Hello, welcome to the first video of a series of video lessons that I hope to bring to you. In this lesson, we're going to be talking about the four forces of flight. This is a very important lesson because there's a basic foundation of aerodynamics and it gives a base to start building your knowledge on. There is some content in this lesson that would possibly be on the written test. And if you didn't know, there is a written test and you have to get at least 70% to pass. Okay, so getting into the first force, lift. There's four forces. They're lift, weight, thrust, and drag. And lift is the force that allows an aircraft to fly. It's the force that holds an aircraft up. It opposes weight, and it is caused by two things. It's caused by relative wind and the airfoil, the shape of the airfoil. And you're probably like, what is the airfoil? What is relative wind? Well, I have this model here, and if you just take a look at the airplane by itself, there's air moving past it. The relative wind is air moving over the aircraft and its surfaces. So the airplane is flying forward, there's relative wind, air moving past it, like that. And the airfoil is the shape of the wing. Well, airfoil is a fancy term that means it's just a cross section of the wing. An airfoil is like a cross section of the wing. So if you look at the wing just like this, it's probably kind of hard to tell from this angle, but it's curved on the top and it's flat on the bottom. And that's a special shape. And I'll get into why that shape is important in a different lesson. But this is the shape of the airfoil, and it allows the aircraft to fly. Now, weight is the second force, and it's the combined load of all of the people, baggage, cargo, fuel, and the weight of the aircraft itself. And it acts straight downward through the center of gravity. So if you look at the airplane like this, the center of gravity is a point, probably right about here, and it acts straight downward, and it's just the center of gravity is the average weight of the aircraft and everything on board. So if you took a string and hung the airplane by its center of gravity, it would balance perfectly. It wouldn't tilt or roll or anything like that. Balance perfectly. Something important to know about the center of gravity is in steady unaccelerated flight, or I guess this is important to know about weight. In steady unaccelerated flight, weight must be equal to lift. The third force of flight, thrust, is created by some sort of engine or propeller working together, or a jet engine, or anything pulling the aircraft forward. So another important thing is, in order to move the aircraft forward, or in order to speed up the aircraft, you must overcome drag. In order to move the aircraft forward, you must overcome drag. That leads us into the next force, drag. Drag opposes any forward movement, and there's two types of drag that you should be familiar with. There's parasite drag and induced drag. So I'll get into the three types of parasite drag. There's form drag, interference drag, and skin friction drag. So the first one, form drag, is drag caused by the shape of things, like the struts, the gear. They're not that don't have to do with producing lift, and they're kind of just out there into the wind. It's kind of like if you were in a car and you stuck your hand out the window, like you did when you were a kid probably. That's parasite drag. That's technically slowing the car down a very little bit, very tiny bit. That's form drag. A good example, like a Lego airplane made of Legos would probably not fly as good as like a model airplane or an RC airplane. There's just, too many extrusions and doesn't allow for smooth airflow. The next one might be a little bit difficult to understand. It's interference drag. This is drag caused when different streams of airflow intersect and cause turbulence. So things like sharper angles on an aircraft. When the body of the aircraft is flat and meets up with the wing, there's actually streams of airflow that intersect, like right in there, right in that little 90-degree angle right there. That can cause interference drag. Skin friction drag. Skin friction drag is caused by airflow over any surface of the aircraft. I mean, it's kind of like if you imagine a sandpaper airplane probably won't fly as good as like a normal airplane, because it's rough. It's rough, and it's disrupts the airflow more. And that's why we do things like polish or paint surfaces of the aircraft to make them more smooth. We want them to be as smooth as possible. So skin friction drag can't be avoided. It's caused by any microscopic imperfections. If you take a microscope and look at the surface of the wing, it's actually kind of rough. Those are the 3 types of parasite drag. And now I will talk about induced drag. This is drag created as a direct result from lift. This one's a little bit hard to understand, but basically as our speed increases, our airspeed, as it increases, like we're getting faster, the wings become more efficient. They become more efficient at producing lift and cause less induced drag. And this will make more sense later on. Now, something important to know about induced drag and parasite drag is as airspeed increases, parasite drag will increase, but induced drag will decrease. And if you look, or if at a slower airspeed, induced drag will increase, will be higher than parasite drag. Parasite drag will decrease at a slower speed. So it's kind of like it creates this this graph. If you look at a graph here, this might make more sense. As you can see, higher airspeed causes more parasite drag and less induced drag. At a lower airspeed, it's the opposite. And if you haven't noticed already, there's this magical point in the middle of this graph. This is a certain airspeed that creates the least possible drag on the aircraft. There's the least amount of parasite and induced drag, the least amount of total drag. And this airspeed is special, and it's on every aircraft. It's called LD max. This airspeed is called LD max. You might be thinking, this is LD max. It stands for the lift to drag ratio. You might be thinking, why isn't it called the thrust to drag ratio? Well, the thing is all of these forces are directly related to each other. So changing one of them will change another one. For example, if you increase thrust, it would also increase lift, because lift is related to the relative wind. So when you increase thrust, you're increasing your speed, and that increases the airflow, which increases lift. That's why it's called lift to drag ratio. The one force that usually cannot be changed is weight. This will change over time, over the course of the flight, due to fuel being consumed, or fuel being dumped, like in an emergency. And when an airplane needs to land and lose a lot of weight, it will dump its fuel. But you can't really do that on a small airplane like this. So the 4 forces are directly related to each other. If I decrease thrust, that will also decrease lift, and will cause a descent to start. Okay, this might seem a little bit confusing. So to hopefully make it more sense out of this, I will demonstrate these in the simulator. Okay, welcome to the Cessna 172 cockpit. Right now we are at 3,000 feet. We are just flying west of the big island of Hawaii. And yeah, we're gonna start by, right now we're in steady unaccelerated flight. I'm just gonna pull back the power, and we're gonna see what happens. I'm not touching the yoke at all. I'm not pulling back or pushing forward on the yoke. I'm just gonna pull back the power. And as you can see, we are descending now. I haven't touched the yoke at all. I haven't pushed forward on the yoke. We just started descending. The reason for that is we lost our wind, our relative wind, since we've slowed down. Since, I mean, the first reaction to that was, of the airplane's reaction, was to slow down. Since when you pull back your throttle, your drag is now greater than your thrust. And that caused us to slow down, and because of us slowing down, we lost our relative wind, which lost our lift. Then, because of the imbalance in lift and weight, that caused us to start descending. Okay, we are back at level flight, back at 3,000 feet. I'm going to demonstrate pushing the throttle in all the way, so increasing thrust. Without pulling back on the yoke, I'm just going to increase thrust. I'll push my throttle all the way in, just kind of correct for left turning tendencies. And there we go, we're in a climb now. I haven't pulled back on the yoke at all, we just started climbing. And that's because we increased our thrust. So our thrust was greater than our drag, and we sped up. And that caused a increase in our relative wind, which caused an increase in lift. And so our lift was greater than our weight in that case. And that caused us to start climbing. Okay, I'm going to get back down to altitude here, since we're above our 3,000 feet. Okay, one last thing I'm going to demonstrate today. I'm going to demonstrate just pulling back on the yoke. We're just going to change our lift. We're going to change our lift without changing thrust at all, and we're going to see what happens. So I'm going to pull back on the yoke, not changing my power setting at all, and look what happens. Our airspeed is bleeding off. We're losing airspeed. We've started climbing because we've increased our lift, but our speed's going away. I've changed something, and that caused a change in something else. That caused an increase in drag. A change in lift will cause, or an increase in lift will cause an increase in drag, an induced drag. And unless you match that increase of drag with an increase of thrust, and also just because our center of gravity was pointing back away from us, which caused us to lose our speed even more, since that force of gravity is pointing backwards. You have to increase thrust in that case to maintain speed. So if I start a climb here, I haven't changed my power yet. Now I'm also going to add power at the same time. Now look at our speed here. Let me zoom in a little bit. Our speed's actually staying pretty much about the same, but we're in a pretty good climb here. So developing this skill of, I guess, managing the relationship between the power and the pitch will help you become a better pilot. And you'll understand how to, I guess, descend. So in the case of descending, you want to pull the power back to maintain your airspeed. So let's say you want to maintain 90 knots. Pulled the power back. I'm going to pitch down just a little bit more to get my speed up, but then pitch back to keep it at 90. So yeah, we're going back to our altitude again of 3,000 feet. And as soon as we get there, I'm going to increase my pitch, but also increase power at the same time, so we don't lose our airspeed. Developing the ability to manage that relationship between power and pitch, and to fly at the right airspeed that you want to fly at, is crucial for being a pilot. And with more training and experience, if you're a student pilot watching this, The more experience you have, the more intuitive that will be. And that's it for this lesson. If you enjoyed this video, please give it a like and maybe subscribe. This is just my first video, but I plan on creating more videos like this in the future. And I hope to have those out soon. Thanks for watching.